Hello, and welcome to the eighth of our 10 lectures. Today's lecture is on nuclear energy, the effects and uses of radiation. So, we start by talking about nuclear reactions. So, in a nuclear reaction, the nucleon number, meaning the total number of protons and neutrons, and the charge must be conserved in these reactions. The mass contained within the nuclei might be different after the reaction, which means that energy has been either gained or released. And so we call the reaction energy Q the net amount of energy that's released. So we have the reaction has the form A plus X becomes Y plus B. Then Q is the initial energy of, or rest energy of A plus X minus the rest energy of Y plus B. And so that's the total amount of energy that gets released. So if the nuclear reaction is exothermic, the reaction releases energy. If the reaction is endothermic, the reaction takes in energy, which means energy has to be supplied from the outside in order for the reaction to take place. So maybe the nucleus gets bombarded by an alpha particle with a certain amount of kinetic energy. And if that kinetic energy crosses the threshold, then if the kinetic energy is equal to the magnitude of Q, then the reaction can take place. And if it's less than that, then there's not enough energy to make the reaction happen. So let's start with this reaction. Determine whether the reaction of deuterium plus deuterium, so two deuterium atoms becoming a helium-3 nucleus plus a neutron, requires a threshold energy. So let's set this up. So we're going to need appendix F again. And so we have two deuterium nuclei. And let's see how quickly I can find that page. Okay, so two deuterium nuclei. And so we have a helium nucleus with one neutron, and then plus a free neutron. And so we're asked to determine if this requires a threshold energy. So is Q negative? So Q is equal to the mass of H plus the mass of H minus the mass of the helium and the mass of the neutron. So times C squared. So we're given these in terms of mass units. So we can write that as 2 times 2.014102. So that's the mass of deuterium minus the mass of helium-3, which is 3.016029. And then minus the mass of the neutron, which is minus 1.008665. And then you're multiplying this all by, so these are mass units. And you're going to multiply this all by the conversion between mass units and electron volts. And so that's 931.49 mega electron volts per atomic mass unit. And so that gives the amount of energy either released or absorbed in the reaction. So that's 2 times 2.01 0.014102 minus 3.016029 minus 1.008665. And it's a positive number, which means it's going to release energy. So it doesn't require a threshold to happen. And so you get 3.270 mega electron volts. And so that's the threshold, or I mean, that's the Q, the amount of energy that gets released in this particular example. So now let's move on to another example. So is the reaction N plus 238.92, so N, a neutron, plus uranium-238 equals uranium-239 plus a gamma ray, possible with slow neutrons? So let's figure out the Q value involved. And the Q value won't necessarily, we won't include the gamma rays in the Q value, but we want to see if we release enough energy that we can produce a Q value. And so let's clear this. And so it's a neutron plus and 92 becomes uranium-239 plus a gamma ray. So we'll do Q, and again, the Q won't include the gamma ray because we don't know how much energy that would have. We know that it would take quite a bit of energy to produce a gamma ray, but let's see, can this be done with a relatively low kinetic energy neutron is basically what it's asking. So we have 1.008665 U plus, and then the uranium-239. That's 239, rather 238, excuse me, 238.050788. And then you're subtracting from that the mass number of the neutron, which is 1.008, or rather, no, you're subtracting from that the mass of uranium-239, which is 239.054293. Yes, and it's criminal that the ice cream truck is driving past while I record this, but what can you do? So that's 939.49. And again, mega electron volts per mass unit. And so what do you get for Q? So you add the first two terms. And so you get 4.85 mega electron volts. And so the question is that massive enough to get a, to produce a gamma ray? And the answer to that, see, I have to go back and find out what the gamma ray's typical energy is. And it's, I've got that written down somewhere. So gamma rays can be on the order of 4 mega electron volts. So the answer to this is yes. If it were on the order of regular electron, simply electron volts, the answer would be no. You couldn't produce a gamma ray with this. But a low energy neutron could produce this kind of reaction with a gamma ray emitted as a result. And so this is an example of gamma radiation. Okay, so now we get to a new term. This is called the cross section. And it's basically the measure of the probability of a collision happening. And it's typically measured in units of area. And it's very tiny units of area. And so it's not unusual to be on the order of something like 10 to the 28 square meters. So often you'll see the cross section expressed in a unit of a barn, which is 10 to the 28 square meters. I forget which scientist said this, but in the nucleus, 10 to the negative 28 square meters might as well be a barn. As far as the cross section goes, and describing a reaction, and the name barn stuck as a result. So one barn is equal to 10 to the negative 28 square meters. So now we're going to introduce the subject of nuclear fission. And so nuclear power is based on this principle. And whether you're talking about the atomic bomb or whether you're talking about energy produced. And basically the idea is you split a uranium atom and the byproducts have less rest energy than the uranium did. And as a result, you're releasing energy. So let's take a look at this. And we have a little bit of a video demonstration of this.
In this video, we're going to talk about nuclear fission. Unstable radioactive nuclei, which occur naturally, sometimes emit strong radiations, especially in isotopes of uranium like uranium-238 or uranium-235. The disintegration converts the uranium isotope into stable lead, and in the process emits energy in the range of 1 to 5 mega electron volts. That's 1 to 5 million electron volts, and even higher amounts of energy can be released by breaking unstable nuclei into even more parts. In 1939, a German scientist named Otto Hahn discovered that breaking up the nucleus of uranium-235 into 2 parts emits 200 million times the energy of the neutron which triggered it. He, along with his 2 colleagues, Lisa Meitner and Fritz Strassmann, found that when the nucleus of uranium-235 is bombarded with neutrons, it will absorb one of the neutrons. This results in an unstable compound nucleus, and the nucleus breaks into 2 equal parts. This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into 2 equal masses, releasing enormous amounts of energy, is called nuclear fission. In the process, uranium-235 initially absorbs a slow-moving neutron, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction. During the process of fission, uranium-236 splits into 2 product nuclei, which are barium-141 and krypton-92. You should notice that a barium atom has 56 protons and a krypton atom has 36 protons. which add up to the uranium atom's 92 protons. The unstable uranium-236 nucleus also releases 3 neutrons in the process. This happens because barium-141 has 141 neutrons, and krypton-92 has 92 neutrons, adding up to a total of 233 neutrons. To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equation of the nuclear fission reaction taking place can be represented by this equation. So as you can see from the equation, 1 neutron combines with uranium-235, forming an unstable compound nucleus, uranium-236. This unstable nucleus splits into 2 stable nuclei, barium-141 and krypton-92. In addition to these 2 nuclei, 3 neutrons are also emitted, as well as a high amount of energy, denoted in the equation by Q. Since uranium-236 emits 3 neutrons in the reaction, these neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amounts of energy being released by a single reaction. So, in this video, we've covered that nuclear fission reactions result in massive amounts of energy being released. Now, these nuclear reactions are most well known for the part they play in nuclear bombs, but they are also an essential part of nuclear reactors, which have the capability to provide mass amounts of energy with relatively low cost. But that's a different topic altogether.
Okay, so getting back to our lecture. So the basic process is, the neutron hits uranium-235 atom. The new uranium atom is very unstable. It lasts about 10 to the negative 12 seconds, basically just barely long enough to warrant a mention, before it decays into 2 lighter atoms plus energy plus more neutrons. And the neutrons are the key to this, because the released neutrons have enough energy to bombard other uranium nuclei and start the process all over again, which in turn releases more neutrons, which bombard more uranium nuclei, and that's a chain reaction. And a completely uncontrolled reaction results in an atomic bomb. A controlled reaction allows you to limit how much energy can be released at once. And so, nuclear power plants work with that. And so typically the amount of energy released by the fission of a single heavy radioactive atom is about 100 million times the energy released in the combustion of 1 molecule of the octane used in gasoline engines. So we're talking a very huge difference in terms of energy per molecule. So what is the energy released in the fission reaction of equation 42/5? So we go to, that is on page, if you want to look it up. And I've got to find it myself. It's on page 1137. And so we're given the barium and the krypton, and we just need the uranium-235, which is in Appendix F. But we'll write the equation. And so you have a neutron plus uranium-235 becomes barium-141 plus krypton-92 plus 3 neutrons. And you want to figure out the Q value. And remember, we've already been told the film said it was on the order of 200 mega electron volts. So we'll see how close an estimate that is. So again, we start with the neutron. Actually, we don't start with the neutron. We'll just subtract 2 of this value. And we'll start with uranium-235. So uranium-235, that's 235.043930. Barium-141, we are told, is 140.914411. Wait, hold on. That's 235. And the barium, we are told, is 140.914411. And these are atomic mass units, minus the krypton, which is 91.926156. And then the mass of the neutron. And we basically have a net gain of 2 neutrons. So we'll just subtract 2. And so that's 1.008665. And that's multiplied by 939.49 mega electron volts per atomic mass unit. And so we do that, and let's see what we wind up getting with all of that. And so you get 0.186033 mass units, and then you'd multiply that. And you get 174.776 mega electron volts. So a fairly large energy release. So not quite 200, but still very, very large for one reaction within the nucleus. So how many fissions take place per second in a 200 megawatt reactor? Okay, so assume 200 mega electron volts is released per fission. So we have the total power and so we'll clear all this. So the total power is equal to the total number of fissions times Q, and we're given Q, divided by delta T. And we want to, so Q is for one fission. And we're asked how many fissions take place per second. So we have N, the total number of fissions, is equal to the total power, times delta T divided by Q. Now, if power is in watts and delta T is in seconds, that means the numerator is in joules. We're going to want to make the denominator in joules as well. So we'll keep that in mind. So we have 200 megawatts. So that's 200 times 10 to the 6th watts. Our delta T is 1 second. And that's 1 to as many digits as you'd like it to be. And Q is 200 megavolts. So that's 200 times 10 to the 6th electron volts. But then you're converting to joules. So you're going to divide that number by 1.60 times 10 to the negative 13. Or rather, 200 times 10 to the 6th electron volts. You're going to multiply, excuse me, by 1.60 times 10 to the negative, and I just put it in electron volts. So we want 10 to the negative 19 electron volts per joule. And so our answer will then be, so our denominator is in joules and our numerator is also in joules, which is what we want. So that's 200 times 10 to the 6th divided by 200 times 10 to the 6th. And then divided by 1.60 times 10 to the negative 19. And you get 6.25 times 10 to the 18. And so that's the total number of reactions. Okay, so let's talk a little bit more about fission before we move on to fusion. And we're going to talk a little bit in some practical terms here. So with nuclear power, in nature, uranium is about 0.7% uranium-235. So uranium-235 is the isotope that we want. The other uranium elements don't split as easily or with the same amount of energy released. Uranium-235 is what you want. For a power plant, you enrich the uranium, meaning you are able to filter out enough of the less desirable uranium so that you have on the order of 4% uranium-235 in the fuel you're using for a power plant. If you're talking about fuel for a weapon, uranium is about 90% uranium-235. So, you can tell from a sample of uranium, from the enrichment in a sample of uranium, what the people who produce that sample are intending to use it for. It's not actually all that difficult to do that. The major cost of nuclear power plants comes from the construction, not just the complexity of the process, but there have been enough concerning accidents to know that the cost of such an accident happening would be prohibitive in terms of environmental cost, and not just in terms of human land, or human life, but in terms of land that's going to be lost for generations. I mean, you look at the Chernobyl accident, which took place in 1986. There's land in the Ukraine that is basically inaccessible for, it's going to remain inaccessible for centuries. It's going to be too dangerous to grow anything on. It's going to be too dangerous to live there. Ironically, some of the land has been used for solar panels because you can put them there and leave them there and wear radiation suits while you're installing them. But it's the kind of accident you want to avoid. And, that raises the cost of nuclear power. Nuclear power has generated about 20% of the United States electrical power since the 70s. So for about half a century at this point, but it hasn't gone up any further. It plateaued. And again, the reasons, uh, part of the reason is concerns about significant accidents. And part of the reason is that natural gas, the price of natural gas has gone up, or rather down, as nuclear has gone up, and the price of renewables has gone down as the price of nuclear has gone up. Some issues for the future of uranium: the best uranium ore is running out. And so that would make it more expensive, um, to produce um, adequately enriched uranium. And so while there is low grade ore, the price of the power would go up. However, the bulk of the price is still in the construction of the plant. So it's not necessarily a deal breaker, but it's not helping the situation. And Fukushima was the most recent example of what's called a nuclear meltdown, where the container of the fuel melted, overheated and melted down, and the radiation escaped into the environment. And um, in Fukushima, the meltdown was the least of their troubles compared to the earthquake and the corresponding tsunami, but it was a perfect storm of events. And basically, radioactive material is spread across the Pacific Ocean as a result of this. Um, but other issues with nuclear power is what to do with the spent fuel, which is still hazardous. It's still radioactive. And where are you going to put it where it won't be dangerous? And of course, nobody wants to store spent nuclear fuel in their neighborhood or anywhere near their neighborhood. One of the interesting things about nuclear power is that it's cheaper to run than other plants once it's built. So once you take out the cost of construction, nuclear power plants are easier to keep going and cheaper to keep going than coal, for example. A coal plant. And that's an interesting factor to consider when you're transitioning to clean energy, because nuclear does not emit carbon dioxide. And if you treat the the construction as a sunk cost, you're going to pay it one way or the other, and you have it. What do you do with the existing plants? Or do you make a priority of closing the existing plants, and as opposed to as quickly as you would close a coal plant, for example? And so these are things you need to consider. And now we move on to nuclear fusion. The sun's energy is generated by fusion, and we'll talk a little bit more about that in the last chapter, which will be in 2 weeks. Basically, you have enormous amounts of hydrogen in the sun's core, and these hydrogen atoms are moving around very, very quickly, and they smash into each other, and you get helium out of the reaction, although there's a process involved. And excuse me. And so there's a process involved. We'll talk about that in a couple of minutes. And a certain amount of energy gets released. So two nuclei must have a very high kinetic energy to start with in order for them to overcome electric repulsion and start a collision. And this is an important, and it's an ongoing issue where fusion plants, meaning power generation, is considered. That in the 1950s, nuclear fusion was considered to be the energy of the future. And it's 70 years later, and nuclear fusion is still considered the energy of the future, or maybe it isn't the energy of the future at this point. There's been a major practical hurdle that they have been completely unable to overcome in order to produce controlled fusion reactions. in uncontrolled fusion reactions like a hydrogen bomb, you basically set up an atomic bomb to give the hydrogen nuclei, detonate a small atomic bomb to give the hydrogen nuclei enough energy to fuse. And, so you have a small bomb to provide enough energy to detonate the bigger bomb. And, so it's not that hard to create uncontrolled fusion reactions, but um, controlled fusion reactions have faced a large number of hurdles. So let's talk about what the reactions are. So you have two hydrogen atoms make a deuterium atom, or nuclei rather. So that's hydrogen with a neutron plus a positron plus a neutrino. So that's basically beta radiation. Another hydrogen atom reacts with the deuterium to make helium plus a gamma ray. So that's the huge energy release. And then you have two helium-3 nuclei fused to make a helium-4 nuclei plus two more hydrogen atoms. So the total, when all is said and done, is that you have a net input of 4 hydrogen atoms to get one helium-4 nucleus plus 2 positrons, which then, ultimately, at some point collide with electrons to emit energy, plus neutrinos, which are basically energy, plus gamma rays, which are large amounts of energy. And that's the basics of the fusion reaction. So it's been the energy of the future for 6 decades, now approaching 7 decades, but a controlled fusion reaction that breaks even and or that releases more energy than more energy than is input has not been demonstrated yet. So the key to nuclear fusion in terms of power generation is reaching the break-even point, because you need to put a certain amount of energy in to make the reaction happen. And you can get energy out, but the energy you're getting out of these fusion reactions is still less than is being put in. So this major logistical hurdle that, in the 1950s, the scientists and engineers of the time were like, oh yeah, we'll figure that out. But it didn't happen. And it hasn't happened. And, it's not clear at this point that it will happen in a manner that would make it cost effective relative to other forms of energy. But as it stands, in terms of a power plant, you can't even get more energy out than you put in. So why would you even bother? And so that's where we are with fusion. But we'll show another video to explain the fusion process in a bit more detail.
Nuclear fusion. In this video, we're going to understand how 2 or more nucleons merge or fuse together to create something more powerful and meaningful. So let's start by talking about the word nuclear fusion. Nuclear means the process which involves the nucleus, and fusion in English means 2 or more entities coming together or merging together to form one single entity. So, nuclear fusion can simply be defined as the fusion or combination of nuclei. Scientifically, nuclear fusion can be defined as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amounts of energy. For example, lighter nuclei such as lithium and helium, when combined together, form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is phrased in terms of energy release, which is usually very enormous rather than mass. Therefore, the law of conservation of energy is satisfied. Consider the example of two hydrogen nuclei combining to form deuterium. Here, one hydrogen atom combines with another hydrogen atom, giving deuterium, one positron and one neutrino. This deuterium, in turn, combines with another hydrogen nucleus to form a helium isotope. If two such helium isotopes are fused together, the formation of heavier helium takes place. These three steps of a nuclear process, where four protons are fused together to form the heavier helium-4 nucleus and enormous amount of energy, is a nuclear fusion reaction. The chemical equation for this nuclear fusion is as follows. Four hydrogen nuclei, when fused together, give rise to the heavier helium. But how is this enormous amount of energy being liberated from such a seemingly simple nuclear reaction? To understand this, let's first calculate the loss of mass in the process. The starting mass of the four protons is 4 times 1.0078, which is equal to 4.0312 AMU. But the final mass of a helium nucleus is 4.001506 AMU. Therefore, the loss of mass is 4.0312 minus 4.001506, which is equal to 0.0297 AMU. This is equivalent to the energy given by Q is equal to 0.0297 AMU times 900 mega electron volts per AMU, which is equal to 27.67 mega electron volts. Wow, that is a significant energy release coming from the fusion of the four protons. However, in spite of such a substantial amount of energy being released in a nuclear fusion reaction, there are no full-time nuclear reactors built so far for fusion reactions, as it is very hard to control such enormous energy release.
Okay. All right. So that's the basics of the fusion reaction. So there are still people actively trying to create fusion. So you have what's called the tokamak reactor, where you have hydrogen atoms held in place by a powerful magnetic field, and then they're brought close enough together so that they can fuse. So there is a small fission reaction that you bring the hydrogen atoms closer together, and then you have a fission reaction to give the hydrogen enough energy to fuse. Another example is the National Ignition Facility, where lasers supply heat to the hydrogen atoms, or energy to the hydrogen atoms, to get the fusion to start, rather than a nuclear reaction. That hasn't achieved ignition yet. Ignition meaning you've gotten fusion, you've achieved fusion. Break even is when you release more energy from fusion than you put in. And so you have beam fusion, which is you have deuterium atoms are focused into a beam and aimed at targets rich in tritium. So you have deuterium and tritium. It doesn't necessarily break even, but what it does do, you can focus energy using this. Focus energy very intensely using this, and investigate the rocket drill sites, for example. So, it has a practical application, even though you couldn't use it to generate power, for example. And you have liquid hydrogen colliding with muons to produce fusion. But even there, you haven't reached break even. And so any fusion reaction requires an input of energy. And right now, there is no controlled fusion reaction that releases more energy than was put in to cause the reaction. So controlled fusion that puts out more than you put in, or gives out more than you put in, is something, like I said, in the 1950s, the scientists and engineers of the time assumed, well, this is a hurdle we'll get past. And it's 2021, and that hurdle is still there. So let's go to an example before we get to radiation in human health for the rest of the chapter. So show that the energy released in the fusion reaction is 17.57 mega electron volts, or in this particular fusion reaction. So let's set up the equation. So we have two deuterium and tritium. Become helium-4 and a neutron. And we want to see how much energy is released from that. So deuterium is and then tritium is 0.6049, and you're subtracting helium 4, that's 4.002603, and that's all atomic mass units, like, that you again multiply by 939.49 mega electron volts per atomic mass unit. And when you plug all those numbers in, that's 3.01604 minus 4.002603 minus 1.008665, and so you get 0.018883. And so that's 5 significant figures, and you multiply by 939.49, and you get 17.740 mega electron volts. Okay, so that's the amount of energy that's released in that fusion reaction. So now we move on to radiation damage. So that was about nuclear reactions, and we're going to spend the rest of the chapter talking about radiation in human health. So basically, radioactive damage comes when charged particles, and so an alpha particle typically has a charge of +2, that it doesn't bring the electrons with it necessarily. And a beta particle is either an electron or a positron, so that's charged. But charged particles can ionize the atoms or molecules of anything that they pass through. And certainly gamma rays can break up nuclei and changing those molecules. So there are definitely ways that radiation can cause damage to organic tissue, and chemical reactions that alter the chemistry of the living material, or nuclear reactions that alter the chemical properties of the living material, will cause damage. The loss of electrons can break apart molecules, causing significant damage. Interference with cellular processes, damage to DNA. The latter can lead to cancer, for example. For medical purposes, it is necessary to quantify the dose of radiation that a patient is exposed to. So you don't just want to say the patient has been exposed to a lot of radiation or a little bit of radiation, but how much? And so uh, we can talk about uh, decays per second. And so one Curie, named for Marie Curie, the famous scientist from, I guess, about 100 years ago at this point, um, she was one of the pioneers in the study of radiation. But one Curie is equal to 3.70 times 10 to the 10 decays per second. So that corresponds to the activity of 1 gram of radium. So they didn't just pull that number out in random, but that's where the unit of the Curie comes from. So suppliers of radioactive material specify the activity at a specific point in time. So it'll tell you what the activity was at on such and such a date at such and such a time. And then you can use the formulas we talked about last chapter to determine what the and the decay rates for the corresponding material, or the half-life for the corresponding material, so that you can determine what's the activity now. So you can also talk about the amount of radiation absorbed in terms of energy per kilogram. And so 1 rad, which is a common unit, it's not the SI unit. We'll talk about that in a second. But 1 rad is the amount of radiation corresponding to 1.00 times 10 to the negative 2 joules of energy per kilogram of absorbing material. And 1 gray, the SI unit, corresponds to 1 joule of energy per kilogram, which is 100 rads. 1 rad of alpha radiation is more damaging than 1 rad of beta or gamma radiation. And the reason being is that for the same kinetic energy, the kinetic energy is equal to p squared over 2m. And so the momentum is equal to the square root of 2m times the energy. So the more massive the material, the more momentum is associated with it for a given amount of energy. And so, for the same amount of energy, the more massive particle has more momentum. And that's ultimately the reason why alpha radiation is more damaging than beta or gamma radiation. The relative biological effectiveness or quality factor is the amount of biological damage that a certain amount of a given radiation does compared to the same amount of X-rays or gamma rays. So you basically come up with an empirical number defining how much more damage alpha radiation will do compared to the same energy of so the same amount of energy from X-rays or gamma rays. And so we're defining a bunch of terms here. So the effective dose in REM is the dose in rad times the quality factor. And in SI units, if you instead of rads are using grays, it's the effective dose in sieverts equals the dose in grays times the quality factor. The quality factor is dimensionless and doesn't change whether you're using rads or grays or some other units. The average American experiences 360 millirems per year of radiation. So that's natural background and includes periodic medical visits. So, it allows for the likelihood, that you might get an X-ray at some point during the year. But 400 millirems per year above the natural background is considered dangerous. So this 360 includes the natural background. So you don't want to have too many X-rays taken in a given year, for example. But so there's a threshold where above which the likelihood of suffering negative effects becomes noticeable. So the quality factor, so X-rays and gamma rays, it's 1. For beta rays, approximately 1. For fast protons, about 1. For slow neutrons, it's 3. For fast neutrons, it could be up to 10. So the quality factor where neutrons are concerned actually increases the more energy you give the neutrons. And for alpha particles and heavy ions, it can be as high as 20. So so alpha particles are particularly dangerous relative to the same energy coming from X-rays or gamma rays. It can cause 20 times the amount of damage effectively. Okay, so let's move on to some examples. 250 rads of alpha particle radiation is equivalent to how many rads of X-rays in terms of biological damage? So let's assume the Q factor is 20. And so you're basically multiplying the 250 rads of alpha particle radiation by 20, again, going to this quality factor. And so that becomes 5,000 rads. So 250 rads is equivalent to 5 of alpha particle radiation is equivalent to 5,000 rads of X-rays. So in terms of what it can do to you. And, so quite a bit more dangerous. So let's do another example. A dose of 4.0 sieverts of gamma rays in a short period of time would be lethal to about half the people subjected to it. How many grays is this? So let's backtrack. So we have 4.0 sieverts. If we go back to the table, a sievert corresponds to sievert corresponds to 100 rems, and 100 rems corresponds to basically 1 joule per kilogram. So basically 1 sievert corresponds to and so, because it's gamma rays, the quality factor is 1. So we're basically, so in this case, rems and rads are the same thing. And so the sievert corresponds to 1 gray, or basically 100 rads, or 1.00 times 10 to the 2 joules of energy per kilogram of absorbing people. And so how many grays is that for sieverts? So like with gamma rays, again, that corresponds to, sieverts and grays are equivalent to each other if the quality factor is 1. And so for gamma rays, it is 1. So the answer to this would be 4.0 sieverts is equal to 4.0 grays. And it is GY? Yes, it's GY. And yeah, so they're equivalent to each other when the quality factor equals 1. And so basically it's defined to be 1 for X and gamma rays. Okay, so now let's move on to another example. How much energy is deposited in the body of a 65-kilogram adult? Right, this is the, yeah, exposed to a 3.0 gray dose. So a gray, again, is 1 joule per kilogram. So this is fairly straightforward. Um, so, and we're told it's a 3.0 gray dose. And so that's 3.0 GY is equal to 3.0 joules per kilogram. And then 3.0 joules per kilogram multiplied by 65 kilograms, that tells you how many joules of radiation the person's been exposed to. And so 3 times 65 is basically, so that gives you 195 joules, or to two significant figures, 2.0 times 10 to the 2 joules. So that's how much energy the 65-pound individual approximately has been exposed to. So radiation can hurt people, but if applied correctly, it can also help people. Rapidly growing cancer cells are especially susceptible to destruction by radiation. So the challenge has always been and continues to be to deliver the radiation to the cancer cells, but not to the nearby healthy cells, because obviously you don't want to do more harm than good, and you want to minimize the amount of harm you do for the help that you do. The radiation source can be rotated to minimize the exposure affecting a particular region of healthy tissue. So sometimes you have a beam and you can move the source of the beam, maintaining what it's maintaining the location that it's aiming at, but obviously it's probably going to have to go through some tissue to get to that location, but you move the beam around so that the healthy tissue and the tissue you want to maintain is not, one particular spot is not getting all the incident radiation. So you want to make sure that that the incident radiation is spread around, so that there's no location that that gets too much of it, but it still all converges on the tumor, for example. The radiation source can be rotated to minimize the exposure. You have something called proton therapy, where protons deposit nearly all of their energy at the end of their path. The catch is it requires a nearby particle accelerator in order to produce the beam of protons. And, which is easier said than done. It's not a cheap piece of equipment. So, it's usually limited to the very high-end facilities, but, it allows for a more localized attack on the cancer cells. Another example is of radiation being used for positive means is a radioactive isotope that's injected or ingested into the body so it can be monitored as it travels. So you're not necessarily fighting cancer with it, but you're looking to see where the radioactive material goes. And obviously you're not going to ingest, they're not going to ask you to ingest the dangerous amount of radioactive material, but rather a monitorable, an amount of radioactive material that you can monitor, so they can see if there's any blockage somewhere, for example. If it's moving more smoothly in one place, but less smoothly in another place, is there some sort of blockage or obstruction that needs to be dealt with? And so that's what a tracer is. Other ways radiation can be used are for imaging. So X-rays are the most obvious example. Bone absorbs X-rays much more readily than other tissue does. So X-rays can pass through the skin, for example, but they get absorbed by the bone, and that enables that enables doctors to look at the bone without having to open you up to do so. Another example is tomography, where multiple images are taken at different angles. And then a computer can process this into a 3D image. And so that's basically what a CAT scan is. The CAT in CAT scan stands for computerized axial tomography. So again, you have a rotating beam that's moving around looking at the same uh, location from different angles, using radiation. And because you're getting different images at different angles, the computer can process it into a 3D image. So you see structure and you see detail to much more depth than you could with just one two-dimensional picture. Another type of tomography is emission tomography, which involves the emissions of a radioactive tracer. So something is injected into your body, and so you get images, uh, from that. And so again, the computer can create an image from the information it gets. And then the last thing we're going to talk about are nuclear magnetic resonance and magnetic resonance imaging. So more important, very important medical applications. So the energy state of the nucleus splits in two in the presence of a magnetic field. The split is different for bonded and unbonded atoms, which provides information on molecular structure. So again, you can use it to see details. And with magnetic resonance imaging, you can alter the frequency of the light by location. That can tell you something about where photons are being absorbed, what wavelengths they're being sensitive to. And you can use visible light for this, which is much less invasive than X-rays or gamma rays. It's much less energetic. And but you can get good information and good detailed information from that. Okay, so that's the whole lecture for today. So Friday we'll go over problems, and I think it's a computer assignment this week. So I will see you Friday. And if you have any questions in the meantime, you can email me or come to one of my office hours.